I don't know if there's anyone still out there. Anyway, it's a real pleasure today to have with us Professor Chua, who's going to talk on a very hot topic since the book of Wolfram came out last year, A New Kind of Science. And Professor Chua is a very well-known, very renowned professor in the area of circuits. He's got many prizes and awards to his name, and he's been a professor at Berkeley most of his career. He has degrees from MIT and Illinois. And I heard him give a lecture similar to this in Siena in Italy in the summertime, and I asked him if he would be willing to come here and give us a lecture like this. I remember Stephen Wolfram was here last year and gave a lecture on his book, and he had books for sale, and there was a lot of interest in it. And I thought it would be very interesting for people here to hear Professor Chua's ideas on this topic. Professor Chua?
Well, thank you very much. Can we turn off this light so we can get better? Actually, I'm not really going to talk about Wolfram. Well, I will talk a bit about him and many others as well. And so it's not really about his book, but how does his book and other books fit into the framework that I'm trying to explain today. Can we turn off the light? Thank you very much. Now, as Professor Ben just mentioned, this is probably one of the most controversial or phenomenal book published last May. Went on the bestseller list the next month, and since then I've read at least 50 reviews. I've never seen any book had that many reviews, and there were some praises and some criticisms, and I try to match them up here. Many people claim it's a masterpiece, and I think so too. And some people thought it's just a brute force computer simulations, and I thought that's also true. And some people say it's a new scientific revolution. Others think that it says nothing in it is new or surprising, and there is some truth in that as well. Some people thought that the book is comparable in impact to Newton's Principia. I think Wolfram himself suggested that. But other people thought that it's comparable in theme from Shakespeare's Much Ado About Nothing. And finally, a lot of people, including myself, of course, think that's a work of genius, and as well as a work of egoist. So it's a bit controversial. But there is a lot of merit in this book, and indeed, for those of you who you should know better than me, but just in September 4, the U.S. Senate Subcommittee actually have a 1-hour hearing from Wolfram, and usually you don't invite scientists, and one of the very influential Senator Brownback actually came back, and he seems to be committed to finding a home for Wolfram's research, and he says to Nature, which is, of course, everybody knows, he told Nature that it seems like this work could have enormous potential. He told Nature after the hearing, if it is right, then the government should be investing in it. So obviously there is a great deal of attention. But there is a lot of related material that I would like to talk to you about, which is actually what Wolfram is talking about, and in particular this is the area that is called complexity. And we start with Stephen Hawking, who says that next century will be the century of complexity, and I think I would agree with him. But the complexity is a very interesting word because over the last decade there are many books written, and I just want to flash many of this in front of you. Complexity, one of them, and they all got complexity. And most of these books are very interesting books. This is Complexity by Prigogine, as you know, the Nobel Prize winner in chemistry, who just passed away recently. It's all about complexity, and this is another book that is fairly well articulated. And there are more popular books like Frontiers of Complexity, and there is a book by a fairly famous philosopher and computer scientist, Mainzer, Thinking in Complexity. Then there is a famous book by a distinguished biologist, Brian Goodwin, Evolution of Complexity, a subtitle, but the title is How Leopard Changed Its Spots. And you will see how it changed its spot today as well. And there is a book talk about Step to Life by Manfred Eigen, Nobel Prize in chemistry, and this is much related to what part of the thing I'm going to talk about, artificial life. And of course, there is this book that I think most of you know, Gell-Mann, the Nobel Prize in Physics. In this book, let me just copy it. It's called Adventure in the Simple and the Complex. So, in addition to this, all of these books with title Complexity, there are many other books that with some other title, in the sense that are related. In the sense that if you open all these books, you see half of the examples are identical. And for example, there's a book on emergence, and there is a book on operative phenomena. So I'm just giving you some of these keywords that many of you have seen: synergetics, and many more, Snelling principles. But if you open the book, you see half of the examples are the same, and they come from chemistry, biology, all fields. So there's got to be something in common. Okay, so what do these names have in common? Now, I will tell you one thing that they have in common is that they have no definitions. That's one thing, and I can prove to you that this is the case. And the second thing that I have in common is what I want to talk about. But I'll just go back to Gell-Mann, since all of you know Gell-Mann. In this one page that I just picked up from Gell-Mann, you will see the word self-organized, emergence, complex, emergent, self-organized, emerged, complexity appearing many times. And what he did is, because there is no definition and he may not realize it, he used it to want to define the other. And so I call it a classic example of tautology. All right, so what I'm going to show you today, or articulate today, is that in fact, the thing that they are all in common is that they are all what I call CNNs. And I will define that in a few minutes. Now, a CNN is an acronym that could be interpreted in two ways. In the first part of my lecture, it will be interpreted as cellular neural network, because it will be used in the context of brain science. And in the second part of my talk, it will be interpreted as cellular nonlinear network. They all have the same code, but it will be used in other contexts, in particular in all the codes, all the examples that you have seen in all of these books, including Wolfram's. So this will be the second part. Now, so CNN, in fact, as I will show you today, is, I call it a new kind of computing paradigm. And when it is used as form of brain science, it will be a computer. And when it is used in the latter context, it will be used as a new kind of science. So I'm going to start first with CNN as a new kind of computer. And when I say a new kind of computer, I mean a real hardware. And this is the hardware, this chip here that I would like now to pass along. Perhaps you can see that this is a chip that is built in Sevilla, in Spain, has more than 4 million CMOS transistors, is fully operational. It's called a CNN universal chip. So it's not built by Berkeley. There are many people working on various aspects. But what's interesting about, and I want to start with the computer to show you that there are real applications, and because most of the criticism about all of this complexity is that they are philosophies, but we're going to start the opposite around. We don't start from science and go to hardware. We start with hardware and show you that from that we can derive science from that as well. And so now you see that the chip's like a Pentium, but unlike microprocessors, the CNN universal chip is a complete computer on a chip. That chip contains everything, with built-in distributed memories, control and communication units within each cell. It has 128 by 128 cells. It's an array of 128 by 128 cells. It's a massively parallel stored program array computer with optical input and supported by a library of CNN subroutines, high-level CNN language, like C language, a CNN compiler, and CNN operating systems. All of these are available now commercially in Europe. And but what's different about CNN is that it is a different kind of computer, and in fact it is a new kind of computer which is the brain-like computer based on nonlinear dynamics. There's nothing digital in this computer. It never adds any two numbers or multiply two numbers, let alone multiply inverted matrix. To give you a little bit of a comparison on the computing power, why there's so much interest, this CNN chip has been compared for image processing applications, and I will show you shortly. There are several image processing mission critical applications where you would need the computing power of an IBM cellular supercomputer 2002, and that you can do now with this single chip. And for those of you who are not familiar with this IBM computer, it's made up of 65,536 IBM powered PCs. It has a speed of 12 teraflops, and if you add up, you know how much it's pen area for it. There are 64,000 here, all lined up here. If you add about this, we're talking about almost 7,000 square meters of silicon. This bit of 0.5 megawatt of power. Now the chip that you just see now is 128 by 128. It has 120, also 12 tera ops. It's not flop, so it's not a direct comparison, but it is a comparison for the application I'm talking about. It is almost one-to-one. In a sense that you can do the same thing that you would need this computer to do with a single chip. And it has an area, of course, of only 1.4 square centimeter, consumes less than 5 watts of power. So it's a very extremely fast chip. And there's some commercial product. This one is called a bi-eye because it is the first camera that you can actually detect depth information. If you want to design a robot that reaches out into things, he has to know the depth information. This is a camera whose heart of it is a CNN chip. And interestingly enough, it was just voted the product of the year at the most prestigious machine vision fair in Europe. You may not know that, but there is a fair every year for the vision fair, and this is Vision 2003. And this is a group, this was held in Stuttgart. And this product was built in Budapest. So much of the things I'm talking about today are not, in fact, most of the things is not from Berkeley. I'm just relating to you. But what it is that this is an enabling technology. So it's not a competition of anything existing. It's an enabling technology for many mission critical tasks requiring at least 3 orders of magnitude higher performance in speed, power, and area than conventional, and then you can get with conventional technology. Now, so I'm going to show you 3 examples of where this chip is being used or will be used in a very near future. Just 2 weeks ago, all of you know, of course, Secretary Spencer Abraham, he has listed 28 top projects that the USA is going to support, and on top of that is the ITER fusion project. ITER is the International Thermonuclear Experimental Reactor, and I believe it's already been decided to be in France, but a CNN universal chip is presently being used in a small-scale version of that. It's a tokamak reactor in Europe for real-time visual processing of plasma instabilities. Because I don't want to go into any detail of this thing except to tell you that this is just a very small-scale version of the tokamak in Italy, and in typical plasma tokamak is a torus with deuterium and tritium hitting each other, spinning at great high speed. And one thing that can happen is that you can be unstable, and it's a very serious problem. And so presently they are now putting a CNN chip so that you can monitor any onset of instability and to control it before this happens. And the onset of instability, like detecting, this is one example of such a instability in the plasma. So this is an example where you need extremely high speed. We're talking about microsecond speed, and so that's one example where it is an enabling technology. You can do the same thing with the IBM PC, an IBM supercomputer, but now you can do it with a single chip. In 2007, 3 years from now, NASA will launch a Scout mission to Mars. A small plane will be released from high-altitude balloon, unfold its wings, and fly over Mars to detect certain terrains which may harbor waters or minerals. And this is an application where you would need extremely high-speed processing. By the way, the chip that you're seeing, every pixel has already a photosensor. It has antenna, so it's a direct input to the chip, a process on board the chip. One of these chips, if all goes well, is going to be on this NASA plane in 2007. But the most challenging one, as you know, is this problem with neighbor North Korea. As you know, they now can reach San Francisco, where I live. And the problem with this is that you have to detect the launching. You have to try to detect this within the first 5 minutes. Otherwise, there will be a lot of debris and decoys, and it will be extremely hard to do that. And you can appreciate why you need a very high-speed processor, and you appreciate why you cannot have a supercomputer in every installation so you want to detect with infrared and all kinds of radiations and pinpoint the target and try to shoot it down way before it re-enters the atmosphere. And the anti-defense, the task of shooting down, by the way, a missile in space is more difficult than hitting a bullet with another bullet, because such a collision takes place at around 15,000 miles per hour. And but nevertheless, you may already have read President Bush has ordered MDA, which is the former Star Wars fame, to erect 10 rudimentary anti-missile systems in Alaska and California, and they're working like mad now to make that. By December, by this time next year, there will be 10 installations. Most people I talk to think that it's not going to work, and just imagine shooting a bullet with another bullet. And most of you know the football, there's such a thing called Hail Mary pass, and I call it a Hail Mary shot. To be able to really do that in the first generation, nobody really think it will work. But nevertheless, the Missile Defense Agency and DC is working very hard now to design the next generation, and the CNN is one of the major components that most likely will be on it. So these are 3 examples to show you that that the CNN is, that I'm talking about, is a real hardware that is an enabling technology. And in fact, I'm involved in a new movie project, and part of this thing is to be where every cell that you see now is going to have an array of nano antennas. And this is a picture of this nano antenna. This is this bow tie thing that's going to be able to detect radiation from the infrared spectrum over the low, mid, and high ranges of the infrared. And we can pack 25 of these nano antenna within each pixel to sense that, and the signal will then be processed on board at extremely high speed. So this is what CNN Universal Chip is all about. And now it's time to explain what makes it possible. So because it is entirely new technology. What is a CNN then? Well, any collection of locally connected cells which evolves according to some dynamical laws is called a CNN. So that's my definition. And dynamical law could be a differential equation, could be a discrete map, or could be just a computer program, an algorithm. So my concept of a CNN is very simple. You have a collection of cells, and typically cells should be very simple, so simple that you think it's useless. And you couple them, let them interact only within a few neighbors, not necessarily the nearest one, but just a few. And typically coupling should also be simple, otherwise it's not impressive. And the amazing thing is that under the right condition, and the condition is exactly the condition that the cells have to be what I call locally active, which is a principle that I have developed that unfortunately I will not have time to go into great detail today. But a CNN, therefore, in general, I'll say, is just as you have a cube or any collection, and you designate a sphere of influence. In this case, it's the nearest neighbor, but in some case, we may have to have 2 layers of neighbors. And it could be, and you specify the cells, each one to be the evolution laws, and then you specify what's the coupling. So it could be, for example, in the form of a of a buckyball, or it could be in the form of a cylinder. This is, by the way, nature's what I call nature CNN, because it's already made out of cells that form a cylinder that interact locally through its nearest neighbors. It could be a collection along a torus, or just to dramatize the fact, any manifold that you can think of where you make rough cells around it, and the cells are all identical for simplicity. That they don't have to be identical, but the point is make it identical, make it more impressive, and make it easier to build. And you interact locally, and so CNN is just defined by cells and what I call coupling laws. And the only requirement that you can make things happen is that a cell is locally active if and only if it is capable of amplifying infinitesimally small fluctuations in energy. And that's very important, how to be fluctuations in energy, which means you will need to have a power supply. And there's a completely different theory. It will take another 2 hours to explain the detail, but I have a complete mathematical theory, including a constructed method to test whether you give me a cell and I can tell you whether it is locally active or not, at least for an important class. Now, the local activity principle says that a CNN can compute, and that's why you've seen all these examples. It can compute and it can exhibit immense complexity, which is the second part of my talk, if and only if the cells, all their interactions are locally active in a precise mathematical sense that I will not have time to go into today. So, but let me now go back to the chip, because I think many of you here are engineers. It's important to understand a bit of what makes it possible. So let's start with the chip has to be of course in a plane, and so you have an array here. In that chip is 128 by 128. Every one of these red dots is one of those 128 by 128 cells, and it has in the chip it only has a 3 by 3 neighborhood, so it's the nearest neighbor. Some application may need a 5 by 5 neighborhood. There have been several chips already built. They're all 3 by 3 neighborhood. There's one being designed in Taiwan now that's going to be 5 by 5, but it's not yet operational. And now each CNN cell, in the most generous case, it has an input, and input will be a pixel. So typically, you have a grayscale image, so you don't convert it to binary, it's grayscale, and you would lay out the grid of 128 by 128 in this case, and every grid would have a gray lever that generates a certain voltage between -1 and +1 volt, and that is the input to whatever that cell looks at. That's the voltage. So that's the real input, a direct grayscale input. There's a threshold which is a constant that you set that's programmable. Remember, this whole chip is completely programmable. And there is an output. So this is very much like a neuron. This is the axon, and this is the threshold potential of before a cell fires, a neuron fires, and this is the sensor. And then it interacts with the neighbors. So exactly how the chip is very simple, because every cell is made just like this. So let's only look at 9 cells, because there's only one cell in the middle with 8 neighbors. So there is the output, and there's all the inputs. So you got 8 inputs, and each of these 8 inputs in the neighbor is being sensed and weighted by a constant called B, coefficient called B. So there are 9 B coefficients, and we call this the feed-forward synapses because it looks like this neuron. And the output of each cell is also an important source of information. So the output are being sensed and weighted by coefficients called A. So these are called the feedback synapses. So now we have 9 plus 9 is 18, plus a constant, which is the threshold. Every cell has a threshold. We have 19 parameters. And that is every cell is built like that. And the equation of the cell is very simple. So simple you would not believe that it will work. Every cell has only one capacitor inside, and X is the voltage across the capacitor location Ij. It is equal to just a linear. This is all linear. It's equal plus a threshold. Z is a threshold that you can adjust. Plus the input is used with weighted by the 9B coefficients, and the output that is weighted by the 9A coefficient. So this is a linear first order differential equation. What makes it nonlinear is that the Y, the output, is depends on the state, the capacitor, accorded by this simple nonlinearity. That's all. Every cell in that chip that you see is just this, and this is the only nonlinearity. And so altogether you have therefore 19 numbers, 8 parameter, 9b parameter, and 1 threshold. And I will show you now a few examples of what these 9 parameters will do for you. And what I'm showing to you now is that the CNN is a brain-like computer, and the first thing, of course, you now realize it's not a digital computer. And the second thing is that it exploits what I call emergent computation that I will explain later on. But for an important class of applications, a theorem has been proved way back, I did that many years ago, which shows that what conditions of that parameter, and they're very general conditions, where you can guarantee no matter where you begin initially, everything will constant into some kind of potential surface, and where you land is the final answer you read out, and in a chip we're talking about 1 nanosecond. Remember that, that's why it's so fast. In 1 nanosecond, no matter where you begin, no matter what image you put in, it will always in say 1 nanosecond time. And if this is what you want, you decode the coordinate here, and that coordinate will be the answer you're looking for. So that's basically how it works. But that's only one example. There are applications where you don't want to go down, you want it to oscillate, and that's another story that we'll talk about later. So for now, let's just imagine it settles down to either left or right, because the output is a saturation, so it's either blue or red. I mean, in between is where the transient is going around, and the transient takes about a nanosecond, as I said, total. So for example, if you pick these 19 numbers that I showed out here, and you just for simplicity, let me put an input that's a red square, and of course you have a capacitor, so you need the initial condition. According to my color code, white means 0. So you start with 0 capacitor voltage with an input like this, which means all the cells will be receiving 1 volt at T0, and in 1 nanosecond you will get this picture, and this is just the boundary. This is, each one is 1 pixel here. And you can prove that this occurs not just for a square, but for any pattern. No matter what pattern the output will always be the boundary of whatever you put in here. And the way it works is a nonlinear dynamics, because this is the snapshot in time. Imagine now, time 0 is the red square, and based on the color code, it begins to change color like a butter melting in the middle, and eventually in 1 nanosecond, everything is melted, only blue, which is -1, and the information is the red boundary. This is what I mean by, it's not a digital computer, it works by nonlinear dynamics, by flows, like water flowing. And as I say, it's true for any, this edge detection CNN, you can put in any input and it will always get you the correct output. Now let me change this 19 number slightly, in fact, just to dramatize what it can do. Let me change -0.5 to -8.5, keeping the others the same, and using the same input here, where it gives you the edges here, it now gives you a totally different output. You can prove that no matter what input you get in, the output will always be the corners of the picture. So that's why it's called a corner detector. Here's another 19 numbers, and its function, its task is that it will always fill whatever holes there are. In this case, these are the holes with red pixels, and the rest has holes, but they are not enclosed. So only the holes are filled. Here is another 19 numbers, and whose function is to move this pixel, this image one pixel to the right. That's why it's called a horizontal translation, CNN. And here is, I'm giving you some of this example because these are the subroutines that you need to be able to call to solve those initial tracking problems, for example. Here's an example of 19 numbers where whatever initial condition you put here are the pointers where you want to say what images intersects with that. And so in this case, you can see that these 3 points would intersect exactly these 3 birds flying, and those will be the only point object that will be detected. You can imagine how this would be important for decoying and tracking those debris, for example. And there are 2 more important ones that I want to show you. One is called erosion CNN. What this does is that you put in any image, the output of which will be the same image, except one layer is peeled off everywhere, the boundary, so instead of a skinny version of the original picture. If you now change it from -0.45 to +0.5, you get the dual operation. This is kind of mathematical morphology, and what you get is the same picture, but everywhere you add one layer of pixel. Instead of peeling up, you add one layer, so you got a final version of the original. And we are going to come back to use this too again, so that's why I'm explaining this to you now. And so now you realize that this 19 numbers is a program. So that's all there is to it. So let's to emphasize that. And in many applications, it is really like a gene. So I cut them out and I string them out into one string of 19 numbers, and I call it a CNN gene. And so here's an example of edge detection gene. And I always show this picture because Navy is my sponsor here, so they love this picture. And with this gene, it will get you the edges. This is the grayscale input, and it will get you the edges output of this whatever picture you put in. But if I change this number, this gene, to another gene, you notice that the output now of the same picture are only the flat poles, or anything that has minus 45 degrees is the only ones that are detected. And if I change these 19 numbers to another 19 numbers, all it detects are just horizontal directions. And if I change it to another 19 number, it will detect only vertical directions. So in fact, any direction you wish, I can have give you 19 numbers that will do the job for you. Now, but one thing it's important to realize is that once you fix the template, it will religiously carry out that function always, but nothing more. So it looks pretty primitive, but it turns out that this is how our human brain works. Here's an example that led to the Nobel Prize Human Vision found out many years ago. You drill an electrode into a monkey and you show monkey different orientations. And what led to the Nobel Prize was the shocking discovery that if you drive electrodes, say, in this section of the brain, and as you push this downward, you find that the monkey, when it's shown horizontally, will fire. So that neurons recognize the horizontal edges. As you drive a little bit down further, it will not recognize horizontal one, but it will recognize those are a little off horizontal. And if you keep going, you find out that all 0 to 360 degrees, there are neurons that will specialize to do that. And this is exactly the same thing that I just demonstrated to you, And I'm not claiming that this is the same algorithm in the brain, but to show you that there is at least one way to do that, and very simple way at that. And this is how we see. When you see something, the image doesn't go to one part of the brain. We now know that there are at least 32 groups of neurons simultaneously taking the same image and extracting different information and process them together later on to get what we are conscious of. Now, here's an interesting example. All of you know, most of you know Minsky's famous book. The problem here to ask is, are these two objects globally connected? You see, all of the examples I've shown you, you can see essentially it's just local. You don't really need to know far away. Here are two examples where you really need to see the whole picture to see whether it's one piece or two pieces or three pieces. And of course, you know that the perceptron cannot do that. That led to this. It's almost dead after this book was published. So, can we do this with a CNN? It turns out it's very simple. These 19 numbers, and I will show you now this. I'm going to put in the top picture here. And the way this works is that the initial condition is where you knock out a pixel. And you should think of this as equivalent to lighting a fire. Imagine that there are trees all along the red region, and you start one tree on fire. And that's exactly, in fact, how this works. So this is the snapshot in time. And when it is done, when it's finished, when it stops moving, you see that there's something left. So obviously this top picture is not globally connected. Now if you repeat the same exercise now with the lower picture, using exactly the same gene, this is not the lower picture, you knock out a picture here to start a file, and in the end there is nothing left. So it is one piece. So here's an example of a kind of important algorithm that is being used. This is that it works like forest fire. You light it up and you spread the waveforms spread simultaneously, and many of these very fast algorithms that you see in this missile detection and this thing is exactly using this kind of a wave type of thing. It's a bit like a domino effect. You knock off one domino and then it propagates, and we call this computing by waves. So one very easy example to understand is, suppose you want to find the shortest path between 2 points in the labyrinth, and instead of repeating every path, what you do is you start a file from you want to go from point 1 on top to point 2 on 2 and the bottom. You start a file and it will start to burn, and whenever there are branches branching, of course it will branch up as well, and in the end when the file finally reaches point 2, you get you can extract information, and this turns out to be the shortest path, for example. So I've just shown you many examples now of how the single chip, by changing this gene, this 19 number, you manage to do many things. And but there are applications, many applications where you just cannot do it with one gene. Here's a very simple example of a messed up Picasso picture where you got somebody spill some pepper, and it's not so clear here, but there are a lot of black spots here. These are called pepper noise, and there are a lot of white thing that somebody spills some salt, and it got called a salt noise, and there are white cracks. The goal is to repair this picture in the best you can. There are many ways to do this, but none of them is too satisfactory because you invariably sort of mess up the picture. You no longer can recognize the picture very well, and it takes a lot of time. Well, one way now you can do this is, let me repeat this picture, and you take this as an input to an erosion. Remember, the erosion template would peel up one layer everywhere from the boundary, and so naturally all those pepper thing will be peeled off, most of them after one erosion. Whatever that's left, you can put it into the next erosion twice, and practically everything is gone. But of course, when you do that, you at the same time will widen the white area because the gene is completely impartial. Anytime they will just peel up less. So this crack becomes bigger and bigger, and so. But the good thing is that you have no longer pepper noise. So you can now take this output and put it into a dilation, which will now grow back the pixels, and so by 2 dilations, you are back to the original cracks and salt voice without the pepper. And now you can take these 2 and take 2 more dilations, and it will be filling. You will be able to fill up the salt very quickly. And so finally, you can see that this is a pretty good number. It's not perfect, but it's fairly good, except that it becomes spotted because you made 4 dilation versus only 2 erosion. So all you need to do is take this output and put in 2 more erosion so that you're back to the phase that is almost like the original. So you need to solve this problem. You need, therefore, 8 steps. You need 2 erosions, 4 dilation followed by 2 erosions, and which is completely impractical. But if you realize that in a chip this is so fast, we're talking about 1 nanosecond each, you can afford to put a very tiny capacitor that doesn't take up much area at all. And that's what the universal chip is. The chip that you're seeing is not just the 19, but it has a small real estate assigned to that have analog memory and logic memory and some control circuitry. So next is a complete computer that you can program. And this is why it is so fast, because the picture gets sent into the chip immediately without translating it into a binary bit, and immediately processed. And there is an internal program which is designed exactly like a conventional digital computer, so that you would just write a program using the language. It simply says load picture, do 2 erosions, do 4 dilations, do 2 erosion, output picture. That's what you will solve this problem, and that is what the CNN universal chip is all about. Why this is why industry and I mean the mission critical people are doing, because it is so simple and so fast. So the CNN universal chip also, we can prove that it is as universal as a Turing machine, which probably you can predict now that you can see this how this is done. And in particular, a cellular automata which is all the book that Wolfram is about. It's all about cellular automata. It's a special case of a CNN with a trivial program. You simply say load the Boolean function, and you say keep repeating, make a do loop. And so since the CNN universal state can program, where every step you can put in a new template. In a cellular automata, you just use the same template just over and over again. So that's why it is a special case. Okay, and now you might want to know how many of these programs are available. I've shown you about a dozen or a couple of dozens. Well, it turns out that at least there are 2 to the 9, or which from 10 to the 154 distinct Boolean functions of 9 binary variables. This is a huge number, and we have a trivial program that you give me any of these things, the computer will generate the gene. So in that sense, we have already this many subroutines available to write any program you want. And those of you who may not recognize how large is 10 to the 154, here's the comparison. The volume of the universe is 10 to the 84 centimeter. And the mass of the universe is only 10 to the 80 times the mass of hydrogen atoms. So this is an immensely large number, and we have 10 to the 154 genes already ready. And we do not know how to use most of them yet, but they are ready, and all you need is just to program it in. And this is similar in some sense to in biology. In biology, there are many different types of cells in the human body. Each type of cells can give rise to only cells of the same type. For example, a liver cell can only give rise to a heart cell, not to a neuron. But there is a special kind of cell called a stem cells. This is an example of a stem cell. A stem cell can be programmed to function as any type of cell in the human body. And now, since the CNN universal set can be programmed to execute any one of the 10 to the 154 Boolean functions, CNN cells are, I call the silicon analog of the biological stem cells. And so now you can appreciate that you have immense number of subroutines available, and it's just a matter of ingenuity to write a program to make use of them. Now I want to revert back to the fact that this is supposed to be a brain-like computer. So let me go back to show you an example of higher brain function. The fact that you take different edges, those are called lower brain function, very simple. But a higher brain function is that function. A monkey, for example, has been subject to this torture experiment about 10 years ago by Professor Fujita from Tokyo. And he was shown different things, not just a thing, but he was shown the different, and the monkey wasn't, in that particular experiment, he wasn't interested, so you don't see many firings. He was shown a book. He was not too interested, so the researcher thought maybe monkey likes banana, so he showed him banana, and nothing much happened. And then he showed many, and then he showed this little picture, and then all of one monkey went crazy. You know, he started hearing the Geiger counter like a machine gun, clack, 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 clack. It means that neuron really likes this girl for some reason. And now he showed other things, a canary bird, nothing much happened. And then so he showed him a female monkey, and he was not too interested. But he sent the same female monkey, this time this thing, and he went crazy again. So he said sex? Yeah, maybe this eye contact makes a difference. And he then Fujita made many more examples. He from monkeys to rabbits to oranges, nothing happened. And then by chance he showed this fruit, and the monkey went crazy again. So it's not sex, okay? There is something in this monkey and the little girl and the female monkey that that particular is in the up somewhere here a higher level brain that monkey is recognizing, and that's called high. So and it's established that there are neurons that are specialized for different geometries, and now a CNN program has been written using some of those subroutines, and the input is this face with this pepper, and the output are the lips and the part that looks like it. So this is a neuron, a group of neurons in that part of the brain that only recognize certain geometric features. And along this line, we also, this is a pattern that Professor Weber, myself, and Rosca have done. We call this the bionic CN bionic eye. And this is the future, and it's not now, okay? But the CNN, but we had a pattern, by the way. The CNN universal machine can be programmed to mimic different retinas. Program A, for example, could mimic a frog retina. Program B could mimic a tiger salamander retina. C, a rabbit retina. D, an eagle retina. And moreover, we can write an extended retina program which combines all of these features. That is what we would call someday a bionic eye. And so it is entirely possible someday to do this. What we are waiting for is the prosthetics for this to happen. So this is the first part of my lecture, that where CNN chip is used as a new kind of computer. From now on, I will talk about CNN as a new kind of science, and which means that we no longer interested in specific application. You no longer send a missile or a big picture. There is no input in this case. So this is why I call this now CN part as a new kind of science. And so let me switch gear now. So this is the part that I'm talking about now. And I complained in the beginning that there is all of these books in common have no definition. So I better give you one. So my definition is the following. We define complexity as the spontaneous emergence of patterns on a homogeneous array of identical cells which interact with neighboring cells via simple local rules. And so that's my definition now. So in general, you have since there is no input, the cells are all identical. Our intuition would say that the output should be all identical, should be homogeneous. And it is exactly the case when if you can show that the cells can compute in the sense that if it is locally active, then you can actually produce patterns. And patterns should be thought of as information. And when this happens, we call this an emergent computation. The biology will call it emergent computation. In particular, any self-organized spatial and/or temporal pattern which emerges from interactions of identical cells. Remember, the cells are identical, and the boundary conditions are identical. In a homogeneous medium, it's called emergent computation. And what is important about emergence is that the two key concepts. One is that the computation has got to be much more complex than individual molecules of capability, and that the computation should be holistic in the sense that the result is more than the sum of its parts. You can never predict, in other words, what one cell can do, but put them together in the right way, you have emergent properties. So emergent properties are properties of the whole that are not possessed by any of the individual parts making up that whole. And just two trivial examples of emergent property that everybody will understand. An air molecule is obviously not a tornado. A neuron is not conscious, but put them together under the right condition, you have a tornado and you have consciousness. Now, this concept of emergent actually is very deep. And not only about 3 years ago, there is this Nature article talking about gastrulation. I don't know how many of you here know biology, so I'm going to explain you what gastrulation is. And you see that's important for you and me too. This is where you and I all came from. We start with one egg from our mother, get fertilized, and it's divided into four in quick order. And within short period of time, what you have is a balloon made up of all cells, and this is called a blastula. We all came from that state. All animals came from that state. And the important thing is that all the cells are identical, completely identical. So according to my definition, it's a CNN. And the mystery is that, and for reasons that's still not well known, when the right time comes, it's like somebody puts a finger in below, and if I have a cross section of that, somebody will push this balloon up and start to deform it, and in short order, you have the beginning of the intestine of the embryo, and eventually that leads you to you and me. Now this is very frightening, very unexpected, because how can you say something totally identical evolve something for no reason? And one of the deepest person who ever could ask this question is Alan Turing. Most of you know Turing machine. Many of you probably do not know that he also published a few other papers. One of them is a new area called morphogenesis. So what Turing essentially asking is, how can that be possible? And he succeeded to produce a mathematical equation, a reaction diffusion equation, with all the symmetry that we said, and prove that you can actually have answers that are more than uniform. And in fact, this subject of breaking the symmetry to get you a form and structure is called gastrulation. And this is so deep and mysterious that distinguished biologists recently, Wolfram said, it is not birth, marriage, or death, but gastrulation, which is truly the important event in our life. And I think I agree with him, because all the others we understand, but nobody yet understood exactly how gastrulation forms. We have a CNN that will do the same thing. We put the CNN, exactly the same cell that I just showed you. I just arrange them in a ball-like thing, imitating a ball. And so now every ball has only 3 neighbors, of course, so this is now, we have only 4 parameters. You can see this is the same equation. And if you pick those parameters improperly, which means if it's not locally active, you end up with something that you would expect, something that has the same color, no pattern. But by changing the numbers, according to my theory, to make it locally active, you would turn that into something that has color, and that is what we call emergence. Okay, it suddenly now has patterns. Okay, now let me move on to other interesting examples. I don't know how many of you know about force fields, but force fields is interesting because seeing stars is seeing force fields. They are images generated within the eye and the brain rather than by light from the outside. Force fields are patterns of light, dark, and color that you can see when no light is present. And the way you observe force field, you can do that at home tonight. Go home and before you go to bed, just close your eye. And when the reason you want to close your eye, you don't want to see anything, no input. The whole point is there's no input, okay? No input. But if you press it gently for a few seconds, you will see patterns. You may not believe it, but you will see that pattern. But depending on how gentle you touch and position, you will get many different patterns. All of these patterns that is generated with no input in the brain are called force fields. And Professor Austin published an article many years ago, that was in the early days of the LSD, so he took advantage. So he took 75 micrograms of LSD, and he of course began to hallucinate. There's no input, but and when he recovered, he published his paper and he pointed out what he saw. And so this is an example of emergence. Okay, we have a CNN that will do the same thing. Right? Same equation, except that this time we use 5 by 5 neighborhood, make it a little bit more dramatic. It's exactly the same, no change. I think most people recognize that this is very similar to that hallucinating pattern. Okay, so and this can also explain many of these mistakes in the Middle Ages. If you ever been to Venetia and go to the Palazzo Ducale, you will see a very famous altar piece by Hieronymo Bosch, and you can see this pattern. If I magnify this, you will see this end of a tunnel thing. Many people near death that recovered report the same thing. You see the end of tunnel light, some kind of hallucinating pattern, and now we can explain a thing that is nothing but just a change of chemistry. Like the LSD will induce this kind of pattern. So this is an example of emergence, and I'm going to show you more examples of emergence just to show you, because I'm not going to show you any example that you see in all of these books that I've shown you. But I'm going to do it with one CNN, same equation again, 5 by 5 template. I'm going to have a B, in fact 0, no input, just remember, there's no input. I'm going to sometimes put in a threshold, but most of the time it's going to be 0. So if I pick the number say minus 23.25, and you see, I'm going to break it up so that you will see the rest are the same. I'm going to only change this meter number, and I'm going to change Z from 0, the thread from 0 to minus 1 volt. If I do that, I will see patterns that go all the way from stripe, it looks like tigers, to leopards. The book, one of the titles said how the leopard grow its spots. I can just show you now that there is at least one way using a CN to do the same thing. And so these are showing how you can easily get stripes and spots. And I want to show you also another. If I change the meter number and just change it to by tiny bit, I now get a pattern that look like that. And I think you would probably recognize that this is very similar to let me reproduce it here. And this is very similar to a zebra kind of pattern. And it's nothing but that thing that I just showed you. And in fact, just by making the cells locally active, I can convert now to this picture earlier that has one color. By making it locally active, I can have what I call a zebra bottom here. And it is a two-dimensional CNN. Now, using exactly the same template where you saw the spots, it's interesting. I don't know how many of you are perceptive enough when you went to the zoo. You may or may not realize that if you look at a leopard, that the tail of the leopard is not all spots, but toward the end it's made up of stripes. The spots are way up here. And the question is why is that so? Well, it turns out that if you use exactly the same template that I just gave you to give you the leopard spots, except that instead of all the examples have been rectangular, this time I make it a trapezoid, just changing the shape of the CNN, that's what it gives you. You got stripe in the end. So it's just a natural consequence of the dynamics, or if we want to be more precise, it's nothing but mathematics, doing the job. And if I change this 19 number and this 25 number slightly differently, I will get patterns like that. And those patterns are seen in many places. Here are some sand dunes you find in the Sahara Desert. I think you could recognize those stripes and forks. And if you look at interfaces, you can see those what I call tuning forks, and there are all kinds of stripes. And the reason I'm showing you all this is that not many of these examples are you find in those books, and they are totally unrelated. So the point, what moral here is that if there is going to be an explanation of how patterns arise, it better not depend on just physics or chemistry, because it appears everywhere. And I'm telling you now that it's nothing but just nonlinear dynamics, because that is the only language that is universal, that you can complain to say that you are not a physicist or you're not a chemist. It's just straight out of the CNN dynamics. That's one of the main messages today. And now I want to show you changing that to minus 24.2. Not much, nothing much. I will get you patterns that look like the following. And if you look a little bit closer in this picture, you will see that they are just hexagons, made out of hexagons. So these are the CNN hexagonal patterns. And I show you this because hexagonal patterns are the favorite example you see in all of these books. And in particular, these are honeycomb patterns that you will see. They are hexagons. These are if you magnify your cornea in our eye with a microscope, you will see that it actually is not uniform but made up of honeycomb-like structures. If you magnify insect muscles, tiny insects, and you look at the muscle part, you will see that they are made out of hexagon. If you magnify the eyes, the compound eyes of flies, many insects have this compound eye. If you magnify that, you will see they are made of hexagons. And many of these examples you will find in many of these books. Go to Sahara Desert, and under right side condition, you get big structures like this, but they are hexagon if you look from way above. You go to Tibet, and under the right condition, you got landscapes that looks like they're all hexagons. So I think the point of showing you all these examples is that not only you see these examples in most of these books repeated, but there had to be a common explanation that will give rise to this pattern, and those explanations should be discipline independent. Here's the last example. By changing it to minus 21.9 and 0 here, I can actually grow, starting from a sheet like that, and if I keep iterating in time, let it go in time, it will grow into a crystal, in particular into a dendrite. These are dendrites. And so I've just shown you that I can produce dendritic patterns, and this of course I have a square symmetry, and there are many patterns in nature. This is from IC technology, new nanotechnology. This is the kind of pattern you can get. It's dendritic. Here's a picture that looks like trees, but this is the delta of the Colorado River. And above all, snowflakes or dendrites. All this possible. And I'm out of time today, but otherwise, it's possible to fine-tune this concept into what I call edge of chaos. And the edge of chaos is a region in this parameter space where it tells you where is the most likely coordinate, likely source of parameter where you can have real complexity. But that is the story for another lecture. And for the remaining part of my time, I want to sort of quickly go over to you. Remember the concept of C, and so far all of these examples are based on one cell. The equation, the trivial equation. But my definition of CA is very general. It's just any cell. You can define your own dynamics. All you need to do is tell me what is the evolution law, and provided the evolution law is locally active, and you tell me what the interaction and what is the spheral influence, you have a CNN. And now I will show you many examples where I use other kinds of cells. One of them is hyperacuity in time, and this is very fascinating because the barn owl, most of you know what a barn owl is. This is barn owl here, it's in this cover, Scientific American. Barn owl can pinpoint the exact location of a moving sound source, such as a mouse, in total darkness better than any other animals. Its neuron can respond to sounds from the 2 ears in such a way as to provide the owl with a very detailed and precise map of the space in front of it. Even though the individual sensing neurons have a rather slow response time, which means hundreds of milliseconds, a proper collection of neurons, that is a CNN, in my definition, is capable of extremely fast computation, which means in microseconds. This emergent computation capability is called hyperacuity in time. In other words, the barn owl literally sees the world with its ears. It doesn't, it has eyes, but that and it put to you, a colleague of mine from Caltech, Berkeley, had this wonderful experiment here. His barn owl in total darkness. This is a time exposure, multiple exposure. He's catching a mouse, and it's in total darkness. So that therefore, obviously, the eyes is useless. But every time he will cut the mouse, as you will see in the cover picture. And the way it works, Professor Kenishi had discovered, is that the mouse, as he moves from left to right, the distance to the left ear and right ear is slightly different. And if you calculate the time, it is in the order of 10 microseconds. You need to be able to detect 10 microseconds to be able to distinguish that the mouse is moving. And yet the neuron is only 50 to 100 millisecond time, 1,000 times slower. And yet, how does the mouse do it? You know, and that's emergence. We have a CNN that will do the same thing, except that this time it's a little bit more. This is now a cell that will oscillate, and I said this is now the CNN, and where every cell is an oscillator, and as the mouse goes from left to right, the thing will file up. So I have just show you that the concept of emergence, where the individual cells are totally incapable, and yet you can do quite fascinating things. Now, there are other examples of hyperacuity. For example, we also have a CNN that will do what an electric fish. Electric fish is an object, a fish that's very primitive. It has a line of neurons. It's so primitive that the distance it's swimming in total darkness, and it depends on electromagnetic fields to know whether you have an obstacle or a predator near you to evade action. But the sensor is so poor. This is a sensor of the electric fish. It's a bell-shaped thing, and the bell-shaped thing indicates the output strength versus the distance from the origin. If the object is about this distance, pretty good. But when you're near the origin, you can see it's almost flat, which means there's no discrimination. You don't really know how far it is anymore. How can an electric fish manage to survive with such a poor instrument? Well, it turns out that all you need is a one-dimensional CNN, where you have a spheral influence that has 7 cells on its side, And you can see that if I have each one individually pretty bad, but if I weight them with the synapses, with 3 only, I already get a better one, and with 5, I get an almost straight line. This is sort of one of the mechanisms to show you how you can get something that you don't get from individual cells. Now, and here, if you pick, just to demonstrate that the theory, there's nothing special about the cell I showed you earlier. It's only special because those are that cells are so simple, you can build a chip. But the concept here, and from now on, is paradigm, so we don't really need to build this thing. And in fact, this after is built. We have a CNN cube made up of this circuit some years ago that produces chaos. But you can tune this so that it's not chaotic, and you can show that under the right parameters. Now remember, this is all coupled by a grid of resistors. And the grid of resistors do nothing but just dissipate power. So if you are going to produce any complexity, it had better come from this cell. You had better be locally active. And when it is locally active, this is what you can see these patterns, which are helical coil things, and rather than homogeneous, this is three-dimensional pattern. In a two-dimensional case, you can have waves like this, and this is the wave that you will see later. In the end, I will show you a short video. This is the kind of wave that is created in this demonstration. You can have a three-dimensional scroll. These are called scroll waves, and these are all from this same CNN. Professor Dito, actually, this is coordinated from Professor Dito that many of you know. Actually, used 500 curve by 500 curve the circuits, and he was able to show you get spatial temporal chaos. You know, and of course, you can easily produce another cell, and you can generate by reaction diffusion equation this pattern that you get from snares. And almost every pattern you get from snares is just a matter of choosing a locally active cell that will do the thing. So and it is easy. It's extremely robust, so nothing special about a particular equation. Now I want to change gear a little bit to show you something a little bit outside. So far everything is about science and about biology, but now I want to go to a bit of sociology. So let's look at ants. You know, ants are actually, this is a wonderful book, but most of you may not realize ants are pretty dumb things. You know, you can almost nobody has ever demonstrated he can teach an ant to do anything. For example, even when an ant is starving and you put an ant and you put sugar cubes always on the right side of the fork, the ant will never, learn. Even though he's starving, it's just to prove how dumb the ant is. But the interesting thing about it is that if you have a few ants, what the ants would do typically is that they would just conduct random walks. And if there's only one ant, you see that it will walk for a little while and then it will rest for maybe a little while and then it walk again. But you can see it's completely random. There's no fixed interval. If you now put in say 10 ants, it's still and add up all those times that they walk and not walk, you can see it's still pretty random. But if you go to about 20, then it gets a little bit more regular. But finally, if you go to about 100 ants per square inch, per unit area, all of a sudden you see the pattern activity becomes periodic, about 25 minutes. So all of a sudden, when you have enough 100 ants or so, the ant decided to take 2 coffee breaks every hour. They would just do that. So this is a good example of emergence. Every ant is so stupid, but if you put enough of them there, you have emergence. And we have a CNN that will do the same thing. Some years ago, Professor Roska designed CNN, and when you don't have enough cells, you see the spectrum of this is chaotic. But if you now have a bigger colony, now you can see they are periodic. This is the spectrum. So you can have a CNN by choosing the right locally active cell. You can make it behave like ants. And so this is an interesting mole. One of the things you learn today is that mole is different because many interacting cells can give rise to extremely complex phenomena which no single cell can predict. And this has been dramatized by no one else than Philip Anderson, the Nobel laureate, who's trying to relate to physics. When you do condensed matter physics, this phase phenomena requires a minimum number. And this is one of the interesting code that I copied from him. He said that a dialogue in Paris between Fitzgerald and Hemingway goes as follows. Fisher said that the rich are different from us. And Hemingway said, yes, they have more money, so more is different. So to dramatize that what emergence means is that you have identical things, very simple things, but more is different. Now the next example is interesting, and let's go to play games. We're going to talk about the prisoner's dilemma game, but I'm not sure how many of you know what a prisoner's dilemma is. So for those of you who already know, please excuse me. Imagine now you have two prisoners. This tape was made some years ago. So you have two CIA agents caught by the KGB. I would have changed if I have time to two Al Qaeda agents caught by the CIA. But anyway, the story is the same. So each agent is being interrogated by KGB agent in separate rooms. Each one is offered the following options. You can either defect, which means that you defect on your friend and squeal, and the second agent would cooperate. In that case, agent 1 goes scot-free, and the agent 2 would get 30 years in prison, maximum penalty. Or if both would defect, both would get only 20 years, which is still a lot. But if both would cooperate, both would get only 10 years. And so where is the dilemma? The dilemma is following: will the two agents cooperate, because they would then get only 10 years? But if one agent defects, the second agent who cooperates will get 30 years. So therefore, if you are the second agent, your optimal strategy, we're playing game here, so you want to see what the optimal strategy to win. The second agent ought to have defected. In fact, even if the first agent would cooperate, the second should still defect. That should be the optimal strategy, because this option sets him free. No matter what the first agent does, the second's best strategy is to defect. But the first agent is in exactly the same position. Hence, both agents would choose to defect, and each would get 20 years. So why did not they cooperate? And this is the essence of the dilemma. Because the prisoner's dilemma, the prisoner should highlight the difference between what is best from an individual's point of view and from a collective. And now we can see where the connection is. Collective means a collection of CNN, okay? This conflict endangers almost every form of cooperation, including research cooperation among professors. Because the reward for mutual cooperation is higher than the punishment for mutual defection. But one-sided defection yields a temptation greater than the reward, leaving the exploited cooperator with a loser reward even worse than punishment. So the best strategy is always to defect. Mutual defection is the optimal strategy. But many animals do not do that. Bats, for example, vampires, frequently engage in acts of mutual help and cooperation. A bat, for example, that feeds successfully on blood from horses will share its nourishment with an unfed companion by regurgitating a portion of its stomach content. They will cooperate. They are altruistic. They don't follow the optimal strategy. So the prisoner's dilemma is a universal concept, in fact. It occurs in biology, in psychology, sociology, economics, and law. For example, the tension of the early nuclear era are considered a classic illustration of a prisoner's dilemma. The prisoner's dilemma is apt to turn up anywhere in a conflict of interest situation. Study of the prisoner's dilemma has great power for explaining why animals in human society are organized as they are. It is one of the great ideas of the 20th century, simple enough for anyone to grasp, and of fundamental importance. Now, we can turn this prisoner's dilemma into a game. The way to state that is so between two persons. But when you talk about evolution now, population evolution, you can borrow this and convert it into a game. It is one of the most widely studied evolution and game theory. I mean, we didn't generate this, but the game theorists did, and the population scientists did, concerning evolution of cooperation in population surface individuals. Let us imagine a population where individual players occupy small cells in a spatial grid. Now this is what I see in coming. Imagine now you have a grid, except that every cell there is an individual. And the game is played among neighbors. The payoff may be thought of as being related to reproductive process. More successful strategy having more offspring. The spread of successful strategies can be due to genetic transmission, genetic offspring, generation offspring, or cultural transmission, for example, the limitation of successful behavior. It is currently being investigated extensively in economics, ecology, sociology, arms control, etc. And we now have a CNN that will implement this prisoner's dilemma. And so C is for cooperation, D is for defection. If two cooperators meet, each receives a payoff of magnitude PCC. So that's the payoff. So we have here is a payoff matrix. For those of you who know anything about game theory, you always have a payoff matrix. And I notice my time is running, so I'm just shortcut myself to tell you that you can define a payoff matrix, and you can have a game that essentially implements the game of prisoner's dilemma game on many individuals, not just two. And the fascinating thing is that under that condition, there are different consequences depending on the initial condition and how you group together. For example, blue are the nice guys, you know, and red is sort of the defectors. And you can have, under certain conditions, a single defector over time could infect everybody and make everybody defect. On the other hand, if you are within a company of defectors and you are you want to cooperate, you're a nice guy. But if you don't know what you're doing, you're going to be wiped out. After, you know, in few steps you've all become defectors. But even here, these are the cooperators, but you get wiped out. But if you cluster yourself, say in this way, 4 by 4, the blue one are the cluster of cooperators. Even though you're within these defectors, over time you can create your own niche and territory so that you can coexist. And this explains many fascinating things that could not have been explained before, could not explain by just two protagonists. And it can show that you can lead to all kinds of complex phenomena, including spatial, temporal chaos. And the next example I want to show you is that I told you that there are 10 to the 154 Boolean functions that the CNN can implement. One of them is called the game of life. So here's the game of life. If you pick that, call that particular subroutine and say start, do, go on and do loop, you are implementing a cellular automata that is called the game of life. And if you pick this initial pattern, I will show you now that what happens if you have a virus. If you start with a virus, right in this position, everything else is the same. Over time, this is every iteration of the CN of the game of life using this cellular automata version. You will begin to destroy the neighbors, and in short order, the whole thing is destroyed. This is an example of what's called a virus, and a computer virus is just a modern, sophisticated version of this. A computer virus is a program that are hiding inside other programs and are replicated endlessly. It spreads through infection using telephone networks or floppy disks as carriers. Very often, viruses contain logic bombs, programs meant to damage legitimate files at some preordained times. And so what I just demonstrated is that you can have a CNN implementing a game of life to illustrate that what can happen just like a virus. And in fact, each strain of a computer virus can be destroyed, of course, by programming. However, Gödel's theorem implies bad news. The bad news is that Gödel's theorem will tell you that it is impossible to find one debugging system able to exterminate all systems. But the good news are for the students here, people writing virus detection program will never be out of business because it's just impossible. Okay, and this is again a kind of emergence phenomena. The last 5 minutes of my 10 minutes or so, it will be an example, another CNN with another of the 10 to the 154 Boolean function. In fact, it's very similar to the game of life. We just changed a few bits. You start with a single initial condition and let it evolve, and in short order, it evolves into a form, a structure, an emergence from a single initial condition that's completely symmetrical. And I call this a childhood. You're evolving a single organism, single cell organism, and it goes to a maturity stage where it remains more or less the same. And in fact, there is an organism in the vortex C that looks very much like this. This is a real picture of the single cell organism in the Baltic Sea with these rings around and all these jumps inside. I think you can see that it's very similar to that. I try to make this a metaphor of artificial life, for example. And in fact, if you keep iterating this, there is an aging stage, so eventually it implodes and the single organism actually dies. So we can use the same, make the same CNN to just do this. And in fact, going back to one of the examples I showed you earlier where you generate stripes, you can show self-repair as well. For example, if you chop off a starfish arm or a salamander's tail, and the little creature will probably start growing a new one. A wounded zebrafish will regrow almost anything it loses, including skins, bone, joints, nerves, arteries, veins, etc. And it's not so mysterious now. You can see that you can use the CNN that I just showed you earlier. Remember that CNN that can generate stripes? Now, suppose I imitate a wood by cutting out a hole here. So that would be just like you have cut out a piece of the limb. So that is, and with the same CNN, you say go. And this is the evolution. You can see it repairs itself. Okay? And actually for those of you in nonlinear dynamics, it's very easy to understand. Because you stay within the same basin of attraction, you're going to end up in the same place. Now the last example is most intriguing. This is the example where I have, and this is yet another of the 110 to 154 Boolean functions, very similar again to the game of life, not the same but very similar. Start with a random initial condition. You can do anything, just random, and see what happens. And after about say, so you start either like cellular automata. After 11 generations, you begin to develop from a random, completely random thing to something that has a form. I call this an ant-like pattern. And if you keep iterating that, eventually you will end up with something that end up with only this three-legged structure that I call CNN ants. And this CNN ant is always moving from right to left. And let me magnify this. And so this is my ultimate example of artificial life, because we started with something completely random, like the primordial soup that's completely random, and the lightning strikes imparts local activity to it. Same thing here. Because the cells are locally active, you evolve into form. Emergence, an example of emergence. Okay. So but the last part is the most challenging, which is let's go back to Mars now. Just to go back to the beginning. In 1999, the Mars polar lander was lost during its attempt to land on the red planet, and researchers still don't know what the NASA still don't know what went wrong. Conditions on the Martian surface, of course, are never going to be exactly as anticipated, and machines running pre-programmed loading sequences don't have the ability to adapt to unexpected situations. And so you can't just write program and hope that something is going to act properly, because while a computer can be programmed to win a game of chess, it will be very difficult to imbue a robot with enough intelligence to recognize and avoid obstacles like rocks, or tell the difference between a shadow and a hole on the ground. Current robots are stuck with whatever software they had when they were launched. Smart robots must adapt to hostile martial environment. In other words, we must learn how to indulge intelligence. And intelligence, as the last part of my talk, is an example par excellence of emergent computation. And I will show you what's wrong with just following logic. In fact, most of you have seen this sort of example, I'm sure. There's a English to Russian translation. The translation is supposed to be very good. So somebody, the admiral, testing the contractor, they give him the spirit. He said this is from the Bible. Spirit is willing, but the flesh is weak. And so the Russian translation is the following: the vodka is good, but the meat is rotten. Because it's just following logic. You just cannot adequately have the intelligence to recognize that there are side meanings. And so the point of this example is to show that intelligence is, according to the topic, what you do when you don't know what to do. Intelligence is not the ability to follow rules. It is the ability, however, to develop rules in the first place. So you do not just follow logic. So far we just follow logic. And to end my talk, and then I'm going to have a short 2-minute video. I like to show this picture. Let's go back to the grizzly bear. Well, that's some bears there, and there's an old story of a philosopher who runs when a bear charges him and his friend, who happens to be a mathematician, a logician, very logical. And so when he started to run, his friend, his mathematician, said, "It's no good. You will never outrun a bear." It's very, very logical. Okay? And what does philosophy say is that I don't have to. I only have to outrun you. That's intelligence. Okay? And now I'm going to summarize. A brain-like computer is not a digital computer, so that it has emergent computation, you don't know what it is, and finally the last paragraph. It exhibits graceful degradation, which means that the death of a few neurons does not lead to an abrupt failure. And I want to show you a 2-minute video of a 6-legged robot created by a group in Catania, Italy, that has only 6 CNN. And maybe can you hold it for a second? Just can you hold it for one more?
An autonomous walking robot will...
This is very interesting. Give me another minute or so. If you train a cat and lay him on a treadmill and put an electrode here there, and now if you cut his brain stem, you will see that the cat will still do the correct thing, which means that it is local. Because it's vegetable, it's brain dead. You cut off brain stem, and it will still do the right thing. So it's a CNN. It's locally connected. It doesn't have to reach everywhere. And so this is an example of a robot that is local. It's powered by just 6 CNN cells. And so now let's see the video.
Which is controlled by CNN-generated auto waves. In this experiment, self-organized patterns are used to generate auto waves. These nonlinear waves, generated in a network of CNN neurons, drive the robot, replacing the central unit and a computer program. As a result of this control, a smooth periodic motion is followed by the walking robot.
There are only 6 cells. See, not 128, but only 6. One control per leg. Each cell is generating an auto wave that you have just seen.
Graceful degradation of the brain by cutting out certain neurons from the nervous system of the autonomous walking robot. If we take out a neuron, it is possible to demonstrate how the robot remains functional. This proves that even a damaged network of controlling neurons is capable of self-organizing.
So you're now going to have 4 neurons left.
Now, another neuron is taken out. As a consequence, the robot is still functional, only the motion pattern is changed.
That's what graceful degradation means. That's the end of my talk.
So we have time for a few questions. Does anyone have any questions?
I might add that after the session, those of you interested, there will be a video tape that actually shows the real chip operating in real commercial examples. When I show you about the anti-missile, those are much more military. I will show you there's a part of video tape that will show you some real life application as well that will require the very high speed performance of a CNN chip.
So I have a question. Do you have any recommendation for any of us who wants to read the book? It's a very big book.
You talk about Wolfram book. Well, I think it costs only $45. It's worth buying. And I think the pictures are illuminating, and I think he does a lot of good by calling attention that all kinds of things. Essentially, his only message really is that you don't need very complicated algorithm. You need very simple things, and which translate into simple rules. But he didn't realize that what you need something, you need local activity. And when you interact in a simple way, you can get all kinds of things. And that's essentially all these examples for And one of the things you find in this book is that they are, even though there's 1,200 pages, they are just nothing but examples and examples, and they're all done by computer simulations, and there is absolutely no theory, not one theory at all. But on the other hand, it's not a criticism, because many of this really essentially is satisfies Gödel's theorem. You know, it's just that you can't really predict. It's emergent. You just have to run it and see what happens. And so so I think that book is very nice. They give you a lot of nice examples, and so as long as you take it in the proper context, as long as you don't believe everything he says, because one of the problems he gets a lot of people upset is that he claimed that he found everything himself, and that's not true, because many of the examples he run, other people knew it 10 years earlier, you know, and because they were all, I just show you all these books. They contain all the same examples.
Professor Roy.
I have a quick question
Yes.
regarding the last example of the 6 sense and degradation, graceful degradation. Alzheimer's disease, of course, is one of the things that we've all been hearing a lot about, and many studies have been done. And one of the most interesting studies was called, it's been written up in a popular way, called Aging with Grace. I don't know how many of you are familiar with that, but it talks about being able to diagnose from writing samples of people whether they will end up with Alzheimer's or not, and looking after people died on a control population at whether their brains were really influenced by the disease and by degeneration, physical degeneration. Now, does the ideas that you proposed lend any thoughts to that direction?
Well, only indirectly. You know, essentially, the issue really is finding one or more genes, bad genes, that is responsible for that. And those genes, unfortunately, are many of them are inherited, but many of them don't show up until much later. And but there were some genes that were actually directly transmitted from parents. So if your parents have the Alzheimer's, you are very likely to inherit that kind of gene, and then under the right condition, it will trigger, and it will start to do this self-destroying process. So I don't see a direct connection, other than that this is yet another example of emergence. You know, it's just that the emergence in this case means that it's like a virus destroying. You know, all of it. It's all of this uncontrollable spread of local activity. And so I think, and I keep, if there's one message I'm saying today, and that is that when you talk about complexity, I think it is not the best way to think in terms of physics or chemistry, because those, if you can express something, say physics-based, for example, many of those parts you can express in terms of buoyancy force, in the Benard reaction, which is correct, but then you can only explain that kind of part, like the hexagonal pattern, using physics. And deep inside that, there is much more fundamental one at a higher level, and I'm saying the way you begin to look at this global macroscopic pattern, like the phase ratio, you should look at a higher level, and then you start to see there's a more general principle organizing this thing, and that principle is nothing but just local activity, which I did not define, unfortunately, but it's mathematics, because you can see that nothing, everything I say here, you don't have to know a single thing about circuit. It's just this differential equation, and this differential interaction with the neighbors, and that's enough, okay? And so all the pattern is nothing but interaction of like simple, very simple dynamical systems. And if you just have the correct local activity and the correct interaction coupling coefficients, it would lead to various phenomena. And I call it, in fact, we all know what a natural frequency is in linear system. Everything has a natural behavior. Same with nonlinear pattern. You know, even though you have no input, but if it's locally active, it will have a natural pattern. Like the natural pattern may be the zebra shape. You change a number, you will have another natural pattern, just like your natural frequency can change by tuning. So that's really the message, is that there is the ultimate explanation, I believe, in complexity is really nothing but just mathematics, using nonlinear dynamics. Yes?
Back there, Mark.
Yeah, you mentioned that there were 10 to the 156.
10 to 154.
154, sorry. genes, how did you pick the ones that you used to demonstrate the various forms of computation you would found? In other words, how did you discover those? What was the process?
Okay. Well, those examples that I've shown you is you know, a couple dozen examples are first discovered by brute force. You know, in the early day, I did that in '87 with a student, and then about 3 years ago, I had developed a complete theory which allowed me to actually put in what I wanted. Give me the Boolean function, we spit out the coefficients for you. So that's how it solves. So that's why I say, you give me any Boolean function, I will spit out the genes for you. That's the easy part. It's not, that is just like the human genome part, where we don't know all the sequences. Okay, but the big problem in human genome sequence is that you now have sequence, but what does the protein does? What is the conformation? That's the unsolved problem. We have 10 to the 154, and we know they're all giving you different Boolean functions, but until I simulate it and find this artificial life, I couldn't predict ahead of time. And you know how much 10 to the 154 is, you outlast anybody's lifetime. So there are tons and tons of those things that are out there waiting to be discovered, what it does. And it is non-trivial in the sense that I can show you many examples where if you don't know, you don't know, you say it doesn't mean anything. But if you probe deeper, you can say, aha, it's performing some computation. In fact, I have an example like that. You will never, even just like the erosion. If you just look at it, you will never know what it's doing. Okay, so that's the hard. It's just like the protein, very similar, but even harder, because we have a lot more. But the good news is that anytime you find one thing that is useful, the program is ready. All you need is just type in the program, call my subroutine, and instantly you spit out the 9 numbers, or collecting 9 numbers for you.
Let's take one last question from here.
Yes.
So, does the inputs to your CNN machine are real numbers, right? So
Real numbers, right? It is a grayscale.
So you have actually,
That's for the case when there's input. When there's no input, it will be just random initial or whatever initial condition put.
but even though
Yeah, they're all. That's why it's not discrete. So that's why the Wolfram thing is only a special case. It's only a case where we make it discrete. But it's more general.
So how is it only
Discrete.
at 10 to the 154? I mean,
Well, because when I designed the gene, using my approach, it will spit out those numbers that will guarantee, and this is a theorem, these are not just empirical. I can prove to you that within the neighborhood, not just one set of numbers, and within 5% of the number, that you will always do it correctly. Okay? And it will always spit out integers for you.
Whoever can stay a little bit longer is welcome to stay and talk to them more. And there's going to be a little bit more of the video. But for now, I'd just like to thank Dr. Chua again for a very
Anybody who wants to? Yes. Yeah. Distorted, but you will always end up in the right, valley, not valley.